Hello everyone, welcome back to another lecture on trigonometric limits. We want to find the limits of these complicated trigonometric functions. The first one, it says limit of sine of 7x over sine of 3x when x approaches 0. Okay, so it's needless to say that the top approaches 0, the bottom approaches 0, so we do have an indeterminate form here. But what technique should we use? That is the question here. So what I'm going to do, I'm going to say this can be rewritten in the form of sine of 7x over sine of 3x, but then I can multiply the denominator by 7x, and I can compensate that by multiplying the numerator by 7x so that I'm not criticized, and I can multiply the numerator by 3x and multiply the denominator by 3x as well, so that they cancel out each other, and I'm not changing the question basically. And I'm finding the limit of this giant function when x approaches 0. So let's see what is going to happen here. Here we have, first of all, x over x, they cancel out each other. We end up with a fraction of 7 over 3, which is a constant. According to the properties of limits, I can pull this constant out and write it outside of the limit, and that's what I'm going to do. So it's going to be 7 over 3 times the limit of the leftover, but then the leftover is a product, and limit of a product is equal to the product of the limits according to the properties of limits. So I can say this is actually this is limit of sine of 7x over 7x when x approaches 0 times another limit of 3x over sine of 3x when x approaches 0. So that's what I can say. Now here, 7x and 7x at the top, at the bottom and the top, they're not matching. So I'm going to say let, for example, 7x equal to theta, okay? Then if x approaches 0, we can say then theta approaches 0. So instead of saying sine of 7x over 7x, I can say limit of sine of theta over theta, can change the variable, and theta is 7x when x approaches 0. But the thing is that when x approaches 0, 7 times x also approaches 0. So this would be when theta approaches 0. So that's one thing I can say. Instead of limit of sine of 7x over 7x, I can say this is the same as limit of sine theta over theta when theta approaches 0, given the fact that theta is let to be equal to 7x. And I can use the same trick for this other part. For 3x, I can say, for example, let 3x equal to some alpha, and then we're going to say if x approaches 0, then we're going to say alpha also approaches 0. So this means that I can say this is limit of alpha over sine of alpha when alpha approaches 0. We can say that. A substitution, basically, or a change of variable. Now, this limit, limit of sine theta over theta over when the theta approaches 0, is a very famous fundamental limit in the world of trigonometry, and that is equal to 1. Everybody knows that. So it's going to be 7 over 3 times 1. And this other one, if it was upside down, if it was limit of sine alpha over alpha, when alpha approaches 0, would be equal to 1. But now that it's the reciprocal, still you can say the same thing using properties of limits. You can still say that this limit is also equal to 1. So when you multiply, you end up with 7 over 3, and that is the final answer for this limit. Limit of sine of 7x over sine of 3x when x approaches 0 is equal to 7 over 3. In fact, we can generate a formula right here. We can say limit of sine of ax over sine of bx when x approaches 0 is always equal to the ratio of a over b. So we can even come up with a general formula like that. Okay, next example, x approaches 0, cos of 0 will be 1, 1 minus 1 is 0, numerator approaches 0, denominator approaches 0. That is an indeterminate form again. How do we deal with this kind of a problem? There is no sine actually here, so it's cosine, so totally something new. So this time we are going to use a special trick here, and the trick is that I'm going to multiply and divide the top and the bottom by a special expression that is 1 plus cos of x. So we multiply and divide by 1 plus cos x, and you're going to see what is going to happen now. Okay, so when we do that, we end up with limit of 1 minus cos squared of x. You multiply them. X times 1 plus cos x is in the denominator. And it's needless to say that 1 minus cos squared of x is a trig identity, and that is equal to sine squared of x. Everybody knows about that. Because of the Pythagorean identity, sine squared of x plus cos squared of x is equal to 1. So this is what we end up with so far. And I'm going to split this limit into two parts. Once I'm going to say sine x over x, and then once I'm going to say sine x over 1 plus cos x. So I'm going to split the function into this form. Sine x times sine x is going to be sine squared of x. It's the same thing. I just broke it down, and the denominator is also the same thing. Now I'm going to say limit of a product equals product of limits. And this is using the properties of limits, obviously. So this is limit of sine x over x times limit of whatever is left over, sine x over 1 plus cos x when x approaches 0. And this first limit is very, very famous. It's equal to 1, obviously, needless to say. The second one would be 0 over 2, because if x approaches 0, the denominator 1 plus cos x approaches 2, the numerator approaches 0. And what is 0 divided by 2? Is 0. And what is 1 times 0 is actually 0. Therefore, this limit we were trying to find, and initially it was indeterminate form. Now we know that the answer is 0 to that limit. Going to the next question, moving on. Limit of sine of x minus pi over 4 over 2 times tangent of x minus pi over 4 when x approaches pi over 4 is what? Well, if x approaches pi over 4, the top is going to be approaching sine of 0. The bottom approaches tangent of 0, which is 0. So this is, again, indeterminate form. So what we're going to do, we're going to use trig identities again. I'm going to say this is sine of x minus pi over 4. Instead of tangent, I'm going to write sine over cosine, because everybody knows that tangent ratio is the ratio of sine over cosine. So sine of x minus pi over 4 divided by cosine of x minus pi over 4 when x approaches pi over 4, that is what we need to find. Now, simplifying the numerators, sine of x minus pi over 4 cancels out each other. So we get limit of cosine of x minus pi over 4 all over 2 when x approaches pi over 4. And that's what we end up with. Because this cosine in the denominator of the denominator flips up, goes in the top of the numerator after you simplify it. Now, if x approaches pi over 4, obviously the angle in front of cosine would approach 0, and cosine of 0 is 1. So the numerator would approach 1. The denominator is a constant. Therefore, the final answer is 1/2 for this question. I know I may explain these questions fast. I may do these questions fast. I may solve them fast. But the thing is that I have time restrictions, but you can watch these videos 10 times even if you want. So I suggest you do that, and you always pause the videos and rewind it and replay, and then pause again, take notes, and then redo the question by yourself, and then replay again, and then pause and watch it multiple times so that you understand all these questions and how we do them. Because the first time you watch the video, maybe you don't fully understand what it says. But the second time you watch, you understand just a little bit better. The third time you watch, you notice that there were some parts that you missed in the first time you watched. And then after 4 times watching, or at most 5 times, then you fully understand what is going on and how things are done over there. This is another limit. It says limit of 3x squared over sine squared of 2x when x approaches 0. It's needless to say that it's indeterminate form because top and bottom approach 0 when x approaches 0. Okay, to do this question, first of all, the 3 is a constant, I notice. So I can immediately pull that out of the limit according to the constant multiple rule, which is one of the 7 properties of limits we have discussed in the past. So I'm left with x squared in the top, which I will write it as x times x. And the bottom, I'm going to write it as sine of 2x times sine of 2x. At the same time, as you see, I'm breaking down the numerator and the denominator both. So in this case, I should end up with 3 times a limit of x over sine of 2x. That reminds me of double angle formula. That was one of the famous trigonometric identities. So that's 2 times sine x cos x, all right? And then because limit of a product equals product of limits, I'm going to multiply it by a second limit right away. So again, 2 sine x cos x, basically, that's what we end up with. So x approaches 0 in each case. Now, the 1/2 can be brought outside, and for the other one also 1/2 can be brought outside. So what is left over here is limit of x over sine x times limit of 1 over cos x if you break the function down into 2 parts. And for this one, the same scenario, it will be limit of x over sine x times limit of 1 is left over in the top over cos x in the denominator when x approaches 0. So we have 3/4 in front. So this limit is going to be 1. This is going to be 1, because limit of sine x over x when x approaches 0 is 1, but so is the limit of x over sine x when x approaches 0. So we're going to have 1 here, and then we're going to have 1 there. Now this limit, if x approaches 0, cos x approaches 1. So 1 over 1 is just 1, so that limit would equal to 1, and this other one would also be 1. Therefore, the final answer to the question would be actually 3/4. There could be other ways of finding this limit, maybe breaking it down differently, or maybe not even using the trig identity, the double angle identity formula. Now, I don't have room here, but maybe I could have done it like another way. So if you want, I'll erase this part of the board. I hope you will take notes later, and I will do it so that you see that questions can be done in different ways as well. So let me rewrite this. So it's going to be 3 times limit of x squared over sine squared of 2x, right? When x approaches 0. So perhaps I can break it down differently. I can say this is a limit of x here, and then another x there. So that will be x squared. And then this would be sine of 2x, and that will be sine of 2x. And then I can multiply a 2 in the top, and then I can multiply a 2 in the top here, and then I can multiply by 1/4 to compensate for that. So maybe this is another thing I could have done here. And then 3 over 4, because 1/4 comes out, times limit of 2x over sine of 2x times another limit of 2x over sine of 2x when x approaches 0. So this would be another way you can break it down. And here you can let, of course, 2x equal to some theta. And if x approaches 0, then it is needless to say that theta, which is double the x, will also approach 0. So this would be 3/4 times limit of theta over sine theta when theta approaches 0 times itself, basically. So these two are equal to 1, obviously. So 3/4 times 1, that would be 3/4. So this way, you don't even need to use the double angle identity that I used in the other method. So it would still work out. So the point of doing the question using 2 different methods but getting the same answer was that you realize that you can do trigonometric limits using different methods, using different ideas, different trig identities, and so on and so forth. Okay, so the solution is never like unique. It's not like you can do it only in one way. All right, some ways might be shorter, some ways might be longer, but at the end of the day there are different ways of finding the limit. Okay, I hope you understood how we take care of trigonometric limits, and please keep practicing.